Think about this for a moment. A machine weighing 20 tons, with no wings, no runway, no fixed lifting surface of any kind, rises straight off the ground and hangs motionless in midair. By everything common sense tells us, that should be impossible. Metal that heavy belongs on the ground. And yet military rescue crews, offshore platforms, and hospital rooftops depend on exactly that every single day. Today, we are going to break down how a helicopter actually stays airborne. I promise that after this video, you will never watch a helicopter take off the same way again. For most of human history, the dream of flight meant moving forward. Every early aircraft, every glider, every propeller plane needed speed to stay airborne. Speed was the price of lift. You traded horizontal motion for vertical support. And that bargain defined everything about how early aviation developed. But there was always a second dream, quieter and more stubborn than the first. Not just to fly, but to hover. To rise straight up from a single spot, hold position over one precise point on the ground, and descend again without needing a runway in either direction. Fixed-wing aircraft could not do it, and for a long time, nothing could. The earliest serious attempt at rotor-based flight came from a machine called the autogyro. Invented by Spanish engineer Juan de la Cierva in the early 1920s, the autogyro used a freely spinning unpowered rotor to generate lift, while a conventional propeller pulled it forward. It could not hover. It still needed forward motion. But it proved something important. A rotating wing could support an aircraft in flight without engine power driving the rotor directly. That insight mattered more than the machine itself. The real breakthrough came in 1939. Russian-American engineer Igor Sikorsky flew the VS-300, the first practical single-main rotor helicopter. It was ungainly, tethered during early tests, and barely controllable. But it hovered. For the first time, a powered aircraft rose vertically, held position, and proved that true rotary wing flight was achievable. Sikorsky's design established the configuration that still dominates aviation today: one large main rotor for lift and propulsion, and one small tail rotor for control. That layout was not chosen for elegance. It was forced by a problem that threatened to make helicopters unflyable from the very beginning. That problem was torque. When an engine spins a rotor in one direction, Newton's third law responds immediately. The fuselage wants to rotate in the opposite direction with equal force. In a fixed-wing aircraft, this effect is manageable. In a helicopter, where the entire lifting system is a massive rotating assembly sitting directly above the cabin, it is catastrophic. Without a solution, the body of the aircraft would simply spin beneath the rotor, making controlled flight impossible. Solving lift had been hard enough. Solving torque while preserving full directional control turned out to be the defining engineering challenge of the entire field. But before we go further into how that problem was solved, we need to answer a more fundamental question. You have probably heard the simple explanation: a helicopter stays up because its rotor blades act like propellers, pushing air downward the way a ship's propeller pushes water backward. That explanation is incomplete. Understanding why it is incomplete is the key to understanding everything else about how helicopters fly. A rotor blade is not a propeller blade. Look at its cross-section and you find an aerofoil, the same curved on top, flatter on the bottom shape as the wing of a commercial airliner. It generates lift by exactly the same physical process as a fixed wing. As the blade moves through the air, the curved upper surface accelerates the airflow above it. Pressure above the blade drops, pressure below remains higher. That pressure difference produces an upward force. At the same time, the blade deflects air downward behind it. According to Newton's third law, if the blade pushes air downward, the air pushes the blade upward with equal and opposite force. Bernoulli and Newton are not competing explanations here. They describe the same physical event from two different perspectives. Lift on a rotor blade is the result of pressure difference and the downward deflection of airflow. That is what holds 20 tons in the sky. The critical difference between a rotor blade and a fixed wing is how it generates relative airspeed. A fixed wing moves through the air because the entire aircraft moves forward. A rotor blade moves through the air because it rotates. On a typical helicopter, the main rotor spins at between 300 and 500 revolutions per minute. The blade tips, traveling the longest arc with each rotation, reach speeds approaching 700 kilometers per hour, relative to the surrounding air. That relative velocity is everything. The rotor does not need the helicopter to be moving forward. It manufactures its own relative airspeed through rotation alone. That is why a helicopter can hover while a fixed-wing aircraft cannot. And that rotational lift is the foundation on which everything else is built. Rotational lift explains how the rotor stays airborne. It does not yet explain how the pilot controls where the helicopter goes. For that, you need to understand blade pitch, the angle at which each blade meets the oncoming airflow as it rotates. Change that angle, and you change how much lift each blade produces. Control that angle precisely across every blade and every position in the rotation cycle, and you have complete authority over the aircraft in 3 dimensions. There are 2 separate pitch control systems on every conventional helicopter, and they work together to give the pilot that authority. The first is collective pitch. When the pilot raises the collective control lever, the angle of attack of all rotor blades increases simultaneously and equally across the entire rotation cycle. Every blade bites deeper into the air on every pass. Total lift increases across the whole rotor disc. The helicopter climbs. Lower the collective, and all blade angles decrease together. Lift drops below the weight of the aircraft. The helicopter descends. Collective pitch is the helicopter's primary altitude control, straightforward in concept, demanding in execution, because any change in collective also changes the torque load on the engine and requires immediate compensation from the tail rotor. The second system is cyclic pitch. Instead of changing all blade angles equally, cyclic pitch changes each blade's angle of attack progressively as it travels around the rotation cycle. One blade reaches maximum pitch at the front of its arc and minimum pitch at the rear. The result is that lift is not generated equally across the rotor disc. One side produces more lift than the other. That imbalance tilts the entire rotor disc, and with it, the direction of thrust toward whichever side the pilot commands. Tilt the disc forward, and the helicopter accelerates forward. Tilt it sideways, and the aircraft slides laterally. The rotor does not just lift the helicopter, it steers it. Collective pitch controls total lift and altitude. 2. Cyclic pitch controls rotor disc orientation and horizontal movement. 3. The tail rotor controls yaw, the rotation of the nose left or right, by varying its own thrust to counteract or adjust the torque reaction from the main rotor. 3 inputs. Complete 3-dimensional control. That is the mechanical logic of every helicopter flight. Now apply that logic to real flight conditions, and the physics become tangible. Consider hover first. Hover feels like the simplest thing a helicopter does. It is actually the most demanding. In forward flight, a phenomenon called translational lift gives the rotor a meaningful efficiency advantage. Fresh, undisturbed air continuously enters the rotor disc from ahead, improving the quality of airflow through the system and generating more lift for the same power input. In a hover, that advantage disappears entirely. The helicopter sits suspended in its own rotor wash, recycling disturbed turbulent air through the disc repeatedly. The rotor works significantly harder to maintain the same lift. Pilots experience this as a sharp increase in power. Demand the moment forward speed approaches zero. Hovering burns more fuel per minute than cruising at 150 kilometers per hour. Stillness in a helicopter is expensive. Forward flight is where the physics settle into efficiency. The pilot applies forward cyclic, tilting the rotor disc ahead of vertical. Total thrust now has both a vertical component supporting the aircraft's weight and a horizontal component driving it forward. As speed builds, translational lift improves the rotor's performance. Most helicopters reach their most efficient cruise band at speeds between 220 and 280 kilometers per hour. This is a fraction of a commercial jet's speed, but it is achieved with complete independence from any runway or fixed infrastructure. Then there is autorotation. This is the procedure that answers the question every first-time helicopter passenger silently asks: what happens if the engine fails? The answer is not what intuition suggests. The moment an engine fails, the pilot immediately lowers the collective to its minimum position. Blade pitch drops to near zero. The helicopter begins to descend, and as it does, the airflow through the rotor reverses direction. Instead of the engine driving the blades through the air, the descending airflow drives the blades from below, spinning the rotor purely through aerodynamic force. The rotor keeps turning. Lift is maintained at a reduced level. The descent remains controlled. Just before touchdown, the pilot raises the collective sharply one final time, converting the rotational energy stored in the spinning rotor into a brief surge of lift that arrests the descent. The helicopter lands firmly but safely. The helicopter does not need its engine to land. It needs its pilot to act within the first 2 seconds. Every one of these maneuvers, hover, forward flight, auto-rotation, depends on the same continuous active management of collective pitch, cyclic pitch, and tail rotor thrust. Nothing in helicopter flight is passive. A fixed-wing aircraft in cruise requires relatively little correction to maintain stable flight. A helicopter in hover requires constant input. The pilot is not monitoring a stable system. The pilot is the stability of the system. Every second, the aircraft is airborne. That is what makes the 20-ton hover so worth understanding. It is not defying gravity. It is negotiating with gravity, precisely, continuously, and without pause. Every time you watch a helicopter hold position over a single point in a crosswind, you are watching a pilot and a machine conduct that negotiation in real time, using the same physical laws that govern every object on Earth. Not magic, exact calculation and complete respect for the forces of nature. Have you ever wondered why helicopters become dramatically harder to control in high heat and high altitude? I have already made a video about exactly that.